So in Lab 3, we're going to start talking about acquiring data in physiology. So this lab is entitled Physiologic Data Acquisition. And so eventually when you get to ANP2, you'll be making your own experiments, taking your own data, and answering actual questions about physiology. So now we're going to get started with different methods you might use to ask and answer questions. When we talk about physiologic data, we're talking about measuring data about the body, about how the body is functioning. And often what we want to measure are things that we can't actually see. So what we need to do when we are looking to answer questions using physiologic data is figure out how to turn these facts about the body into pictures that we can then hopefully analyze mathematically. Right? We're going to want to be able to analyze our data using different types of statistics. So the way that we do this is by using something called a transducer. So a transducer isn't a specific individual machine. A transducer is any device that converts us from one form of energy to another form of energy. And that's really key when we're trying to collect physiologic data, because we're going to be collecting data about the body, about these physiologic phenomena, by looking at things that we can't see, but that our transducer can measure, turn it into an electric signal, bring it into a computer, and provide pictures and mathematical quantifiable measurements for us. So our transducers are going to convert physiologic phenomena into an electrical event, usually which is then read by a computer. So we might have some setup like this. We'll have, say, a person walking on a treadmill. In this case, we're measuring their breath. We could also measure pulse. We could also measure all sorts of different things. So we have actual things happening in the body. And we can see that this person is hooked up to various machinery. This is because we can see this device strapped to their head. We're going to be measuring, for example, the volume of air coming out here. But you can't see air on a computer. What you can see on a computer, what you can actually register, is electrical signals. So we take this measurement from the body, and in order to read that measurement, we turn it into an electrical signal, which is then attached to a voltmeter and produces a recording on a computer screen. Okay, so whenever we're talking about transducers, we're really talking about any of the devices that we use to take measurements about the body when we're hooking them up to an actual reader. Okay, so when we measure physiologic data, we're going to get graphs like this. What you're always going to see on the x-axis, you'll see time, because we're trying to measure changes in something about the body over time. And then our y-axis, if we're looking at the raw data, the raw output, directly what's coming out of our device that's measuring something, our measurement here is actually just going to be voltage, because we've turned our physiologic data, our events in the body, into an electrical signal. So if we look at just raw data, we're going to get a number in volts. And that's because volts are our measurement for that electrical signal. Now we'll see that we then often convert these volts back into measurements about the body. So we'll then use these volts to calculate, for example, someone's pulse or someone's heart rate. But if we're looking at just the raw data, what we're going to be looking at is just those volts coming in from our transducer. In lab, usually what we would be using to do Lab 3 is something called a plethysmograph. A plethysmograph is a device that senses a change in volume, and we use it to read pulse. We are still going to work with pulse today. It's just we're going to be making manual measurements and doing the same types of calculations we would do if we were in lab using our plethysmographs hooked up to our computers. We're just going to be doing it a little more low tech. Although if you want to try it with an app, I have some I looked up some apps on various different types of devices that can measure some of these same factors in ways similar to what we would see in lab. Okay, so plethysmograph is a device that senses a change in volume. And the way that actually works to measure our pulse is this. So when our heart beats, it's projecting blood out to the circulatory system. So if you're looking at an artery, say an artery in your wrist or something, every time the heart beats, we're actually pushing more blood through that artery in a pulse, the same way your heart beats with a pulse. This actually causes all the arteries in your body, when that blood reaches them, to bulge slightly. You often can't see this, although on some people you can. My arteries are very deep, but some people have ones that kind of stick out and you can see them. But what happens in everyone, whether you can see it or not, is that the volume of the extremities, so the ends of your body, so your fingertips, for example, that's where you would usually attach a plethysmograph, actually increases slightly. So the volume of that piece of your body increases slightly because there's more blood, so it swells a little bit in the same pulse as the heart beats. So the plethysmograph can sense this change. So it senses this change in volume. And then because the plethysmograph is an example of a transducer, it senses this change in volume, converts that to an electrical signal that can then be read by a computer. And we get this graph of voltage changes, which we can then convert into a pulse reading and then use to calculate a heart rate. Our typical resting heart rate, just so you know, as you're playing around with pulse measurements yourselves, the typical resting heart rate is somewhere between about 60 and 80 beats per minute at rest. Right, so as we're doing calculations, hopefully you got something vaguely near that range. And if you're not, we're gonna wanna take a second look at our math. Okay, that's basically it that we have for our little introductory material. And as usual, we're going to go into breakout rooms and work through the lab. That should be it.